So today is all about chords. A chord in a circle is we want to draw a picture of it because I think that's almost always the best way to handle definitions, is sometimes with geometry is just drawing a picture. So a chord is if we have a circle. Let's see if I can draw a nice circle here. Pretty decent. A chord is something that goes from one side of the circle to the other. So if we have this point A and this point B, this is a chord. And that was one of the definitions we had on the first day of this section, of this unit. A chord that goes through the center of our circle is our diameter. And we should probably give this a circle a center. Let's call it center C. So then this line here would be our diameter. A diameter is a chord that goes through the center of the circle, and this is center C. Circle C with center C. Lots of C's. So here are our theorems. We had 3 of them, and then we'll have another one on the back page. Congruent corresponding chords, which if you haven't figured out by now, a lot of the times the names kind of give away what we're gonna be doing with these. So congruent corresponding chords, there's probably gonna be some congruent chords that are corresponding in, where they're matching up on the diagram. So in the same circle are congruent circles, and yesterday we kind of established what we have to know for things to be congruent. For 2 circles to be congruent, they have to have the same radius. The radiuses have to be equal to one another. If that is the case, then we could say circles are congruent. 2 minor arcs are congruent if and only if their corresponding chords are congruent. So if I have arcs AB and CD, and I was to make a chord between the 2 of them, point A and B and point C and D, these 2 arcs are congruent if and only if the lengths of the chords are congruent. So the notation, remember, a curved hat on the top means you're talking about an arc. A line on the top means we're talking about a segment. And when we say if and only if, that's what we would call like a logical statement that really is just saying that you can prove this by going backwards and forwards. So we could start this by saying if our 2 angles are congruent, our 2 chords are congruent, then our 2 minor arcs should be congruent as well. So it works both ways, kind of forwards and backwards. A second theorem that really gives away itself by its name, the perpendicular chord bisector theorem. So perpendicular meaning 90 degrees, bisector, it splits in half, and a chord, we already talked about what that is. So if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So this is only if we're talking about diameter though. So we have diameter EG, and we know it's a diameter because it goes through from one side of the circle to the other, and it goes through our center. So if EG is a diameter, and EG is perpendicular, we use the upside down T symbol, perpendicular to DF. Perpendicular also means 90 degrees, so if we have this 90 degree angle here, then HD is congruent to HF. So that is our chord being bisected. FD would be our full chord. And then we're bisecting that into 2 pieces. So our 2 chords are congruent, which would then also mean, kind of using that last theorem, that these 2 minor arcs would be congruent as well. Minor arc GD is congruent to minor arc GF. Our next theorem is the converse of this guy here. It starts by saying, well, if they are perpendicular to each other, then one has to be the diameter. All right, so it's just the statement we had up here flipped. All right, we're flipping direction. So if QS is a perpendicular bisector of TR, so we're not saying that for sure QS is a diameter yet. We're just saying, well, if this happens where it bisects our chord, then QS is a diameter of our circle. And same idea here. These two arcs are still going to be congruent. It's just not part of the theorem because we're using the converse. We're not talking about arc lengths here. All right. So we're going to work through examples using these theorems. And I already look like I have one of them started. So we're looking in the diagram. Circle P is congruent to circle Q because they have the same radius. Kind of giving just some more justification. It's also given that chord FG is congruent to chord JK. Again, you can always kind of just look at the markings to know that. And we're also given that the length of chord, so the length of minor arc JK is 80 degrees. We're trying to find the measure of FG. Well, the measure of FG is going to be equal to the measure of JK. And why that is, if you want to give some justification, is because of this first theorem that we talked about on the top. What was it? 10.6. Because since we can go both directions, if our two chords are equal, then our two arc measurements can be equal. So if you want to say like because GF is congruent to JK. Now I'm talking about the segment. So then the measure of arc FG will be 80 degrees as well, because degrees is the units of minor arcs. So again, 80 degrees. All right, flip to the next page. Now we're gonna get a little more mathy. We're gonna have to do some more solving here. Still using our theorems though. Oh, it's already, don't look at what I have written. That'll give it all away. Gotta erase it all. Large eraser. So let's see what we have here in this diagram. We're trying to find HK and the measure of minor arc HK. So we're given that we have a perpendicular angle So these two lines are perpendicular, saying our diameter, which would be, we could call J, and then I think there was supposed to be an L down here. I cut it off. JL is our diameter, because we know it's 90 degrees, and we know if this is a diameter, we're bisecting this chord. All right, so this would be theorem 10.7. We could say if we have a diameter, our chords are bisected. So we could say HN, the segment, is congruent to NK. So they're both equal to, if we want to give a length for HN, HN is equal to 7, so right here. That's not one of the things we're looking for, though. We're looking for the measure of HK, or the length of HK, which we can get from adding our two 7s and 7s together. So we're adding HN and NK together to get 14, the length of our chord. So we want to fill in this part. It's because we get HN plus NK. That's how we get 14. And then with our measurements, we could say, okay, if these two chords are congruent, then that means their two outside minor arc measurements are congruent as well. So we could say this guy is congruent to that guy. So I'm going to write off to the side. So the measure of arc JH, oops, is congruent to the measure of JK. So then we can set things equal to each other. We can plug in what we know. We know JH is 11x. We know that JK is 70 plus x. And we're going to go through and solve. So this would be quick. Subtract x from both sides. So 10x is equal to 70. Divide each side by x. X is equal to 7. Right, and again, x is equal to 7 is not one of our answers because we're trying to find the measure of HK, or the length of HK, which we already did, 14. So you can go back and circle that. And then our second question was to find the measure of HK. Well, the measure of HK is going to be equal to, we can use our arc addition postulate. It's the length of JH plus the length of JK. Which then, if we plug in x for 7 into both of these, we would get out 77 for each of them. So I got to plug this in before it dies. I got it right from here. All right, so 77 for both of them. And how we get that is by taking, we take 11 times 7, plugging in 7 for x, plus 70 plus 7. That's 77 plus 77, which is then you get 154. So the measure of HK is 154 degrees. And there's your second answer. So again, the biggest thing you could do is kind of just sit and process the theorems as you go. Kind of convince yourself you're using one theorem and why you're using it. The intent of giving you all the theorems, I could just not give you the theorems and say, oh, this you do this, you do this, then you do this. But it's so you're using the theorems as you're working through the homework. All right, because you don't have to memorize them, but you need to know how they work. So with our last one, equidistant chords theorem, in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So what we're saying here is arc CD, chord CD is congruent to chord AB if and only if the distance from the chord to the center is the same. So EF, going from this chord to the center, And then e.g. if these two lengths are the same, then our chords are congruent. Then the second question, I gotta re-solve it too. Normally I do this beforehand, but apparently not today. Oh, I don't have all of it. Boom. All right. So in the diagram, QR is equal to ST, and they're both equal to 16. CU is equal to 2x, and CV is equal to 5x minus 9. We just want to find the radius, though. So QR and ST. Let's start there, since that's the first piece of information we're given. QR and ST are both chords, and they have a length of 16 for each of them. So if you want to write, I don't know, it's hard to write a chord length. Let's say that's equal to 16, and that's equal to 16 too. These are both chords. Why we're going to use those chords, because here in our diagram, W to X is our diameter. It intersects a chord perpendicularly, so we know that QR is bisected. QU will be equal to UR. So if you want to draw your little tick marks in there to show congruence, you can. This here is congruent to this here. And that means we have to split up 16 evenly. We're bisecting 16, so each of these sides are 8. 8 and 8. Next piece, we're going to use our equidistant chords theorem to solve for x. We're going to need to know what x is to ultimately solve for our radius. Hey, stop talking. You're having like a full-on conversation and everyone can hear you. So, equidistant chords theorem is saying that if our chords QR and ST, these two segments are equal to each other. CV and CU are congruent. The distance from a chord to the center, they're going to be the same. So you could say that 2x equal to 5x minus 9. So that's what we'll do as kind of our next step. We'll say, you want to write it out, CU is congruent to CV. If you like writing that to help you kind of set yourself up. Then you plug in what you know. We know CU is 2x, and we know CV is 5x minus 9. And then if we go and solve for x, this is just a two-step. We got to subtract 5x from both sides to start. Let's get negative 3x equal to negative 9. And then, of course, divide each side by negative 3, so x would be equal to a positive 3. So what that does, that x is equal to a positive 3, gives us the distance from a chord to the center. So we plug in 3 for x up here. We know that this is not actually 2x, this is length 6, and so is this. This has a length of 6. So this is up scribbling it out. CU is 6. All right, now we have enough to solve for our radius. And in the picture, this is where kind of like we have to know how to make a radius and what a radius is for this kind of is like the big leap in this problem. Because you may say, okay, well, Mr. Scully, I'm given a radius is C at x, right? But you would have to know the length of x to v and then the length of y to c. Which we could find the length of c to y, but there's not a clear way to go from find this length. Same thing here. We can go from c to u, we know that's 6, but we don't know this extra distance. But if you remember that a radius goes from the center of your circle to any point on the outside, we could draw kind of an infinite amount of radii. So for example, this red dashed line here could be a radius going from Q to C. That's a radius. Let's say that's R. What I'm going to do is I'm going to pull that kind of little piece off to the side here so you can see what we're working with now. So what we made here by drawing that specific radius from C to Q, we made ourselves a right triangle with legs of 8 and 6 and a hypotenuse of R, which is our radius. So since we're given a right triangle and we're trying to solve for hypotenuse, we can use Pythagorean's good old theorem to solve for R by saying R squared is equal to 8 squared plus 6 squared. So then R squared is equal to 64 plus 36. Which when we add those together, you'd get 100. So R squared is equal to 100. And take the square root of both sides. So R is equal to 10. So we found our radius by making a right triangle. So right triangles they keep coming back. We're not going to get rid of them. Kind of I don't know if you want to